All right. Good afternoon, everyone. My name is Yongfeng Zhang. I'm an assistant professor in the engineering physics department. And today, it's my pleasure to introduce our seminar speaker and also a longtime collaborator, Dr. David Andersson from Los Alamos National Laboratory. So David is a well-known expert in the field of fuel performance modeling, and he's also taken multiple leadership roles in different DOE NE programs, such as the deputy lead of the NEAMS program, and also I guess is also the deputy lead of the CASL program previously. And in addition to his leadership roles, he has made significant contribution from technical side in applying atomic level simulations like electronic level and atomic level to study the property of defects in various type of fuels and use that to aid the development of multi-scale fuel performance modeling tools. So his work has led to the publication of over 90 peer-reviewed publications and a much larger number of technical reports. So guys, not much for me to talk about it, and I will give the time to David.
Thank you very much for that introduction, Yongfeng. Before going further, you can still hear me, Yongfeng?
Yes.
Very good. I very much appreciate the invitation from Yongfeng and from Wisconsin to give me the opportunity to present for you today. I really wish I could have been in Wisconsin in person. I was looking forward to it. It should be nice fall weather there, and I heard that's true. Unfortunately, that didn't work out for reasons you're well aware of. Hopefully there is an opportunity in the future to visit for a workshop or something like that. And so with that, I'll get started with my presentation. Yongfeng presented my background, and he explained how I have done a lot of work on modeling fuels for reactor or nuclear fuels for reactor applications. Most of them solid state fuels. That's my main expertise and what I've been doing for the last 15 years or so under various DOE NE programs. During the last few years, though, I've had the opportunity to make technical contributions and do research on molten salts and fueled molten salts. That means molten salts containing either uranium or plutonium. And that's the topic I'm going to cover today. So if you were looking forward to a uranium oxide talk, I apologize, that won't be covered today, but there should be some interesting stuff here. Let's see. So before getting into the meat of the presentation, I would like to acknowledge both funding from Los Alamos National Laboratories LDRD program, as well as the DOE NEAMS program. My presentation today will focus on a lot of the results that I've generated myself with close sort of students and postdocs. However, there's a larger set of collaborators that have also contributed and continue to contribute to this work. Both at LANL, the first couple of names there are modelers working on similar work that I do, but also developing what we call tight density functional theory, tight binding potentials for more efficient treatment of molten salts. I'll say a few words about that later. And the last couple of people are experimentalists, both involved with synthesis of actinide-containing molten salts, as well as their characterization, using everything from neutron radiography to traditional dilatometry. I also have a number of collaborators outside of LANL. Ben Beeler, just as Yongfeng, used to be at Idaho. He's now at NC State, and he's also an atomic scale modeling expert. I'm working closely with him on the problems I'll show, or on the results I'll show you here today. Xiao Yang, also at INL, as well as Jake McMurray, who left Oak Ridge for Kairos very recently, and Ted Bestman at University of South Carolina are also collaborators. So I'm going to start to say a few words about what the NEAMS program does in context of molten salt modeling and simulation, I think that might be of interest to the audience here, and it gives you a little bit of a sort of national DOE perspective on the work. For those of you who don't know, NEAMS stands for Nuclear Energy Advanced Modeling and Simulation Program, and it covers most of the modeling work done for reactors, from thermohydraulics to neutronics, as well as materials. And the work shown in this slide resides under what we call a technical area, and the technical area is called corrosion, chemistry and corrosion, which is obviously very pertinent for molten salt reactors. The idea is to use something, this is a picture created by Jake McMurray at Oak Ridge, and it kind of depicts the multi-scale approach used for corrosion modeling in molten salt reactors taken by NEAMS. And there are no real surprises here. We're generating properties, focusing on properties that are either poorly characterized experimentally historically or difficult to measure experimentally, such as salts containing actinides. We use either first principles ab initio methods or classical molecular dynamics to generate properties such as density, viscosity, thermal conductivity, specific heat, and various thermodynamic properties. Knowledge from that scale, as well as knowledge obtained from experiments. I know you have a good set of, or a great set of people at Wisconsin doing various experimental characterization modeling as well to inform corrosion models. Work going on at the phase field level, where you're looking at the mechanistic aspects of corrosion. Those phase field models need knowledge of thermodynamic information, so that's coming from basically thermochemical databases of CALPHA type. So both of those pieces are developed under the NEAMS program. The idea is then that those tools feed knowledge into more of a system level treatment of mass accountancy. And that's done in a code developed mainly at Oak Ridge called MOLD. And the idea is there is basically to track, not here, you have the picture here shows chromium, which is probably the most important species to track. It's a corrosion product, obviously, but also track fission product and so on, and see where they leach out in the loop as well as where they get deposited. And that would then be coupled to other performance models. The tools that are developed here are all, they are developed under the MOOS framework. Did I hear a brief question there from someone? If not, I think I'll move on. So that's the activities under NEAMS for molten salt corrosion modeling. And my talk today will not cover this mesoscale simulations or the engineering scale simulations. Rather, they will focus on ab initio molecular dynamic simulations to generate properties of actinide containing molten salts. So this slide provides a little bit of background to the work, and it sort of continues what I was describing in the previous slide. So the reason why we're doing these ab initio molecular dynamic simulations is to fill data gaps for chemistry and thermophysical properties. The need to fill those data gaps get larger and larger as you add fission and corrosion products, because those systems are not very well characterized, and they are in many cases tricky to characterize. Despite me emphasizing the importance of modeling and the modeling work we're pursuing, experiments are, of course, I would say probably even more important. But so we work very closely with experimentalists, and the idea is to validate enough data points to gain confidence in the model, and then use the modeling to fill in gaps where we can't do experiments for either cost, time, or sort of harsh conditions. I showed you NEAMS Yellowjacket and mold tools to model chemistry and corrosion and mass accountancy in general. So the idea is to use the ab initio molecular dynamic simulations to fill in data gaps for those simulation tools. And I already told you that the main tool that I am using and I will be talking about today is ab initio molecular dynamic simulations. Those approaches are very good at treating complex chemistry and getting accurate predictions for some properties, such as density and basic thermodynamic properties. There are, however, another set of properties that require much longer simulation times to get good results for, and those include viscosity and thermal conductivity. I won't show any results for those because you can do it with these methods, but it's really challenging. So the approach there is to either use existing or develop empirical potentials, semi-empirical potentials to use for those simulations. There are also approaches that use sort of DFT-based potentials, and I'll briefly mention work on developing tight binding potentials at the end of my presentation. So what I'm going to cover today in terms of material systems is potassium, sodium, aluminum, and uranium chlorides. I'm going to start going through sodium chloride, potassium chloride, a little bit of aluminum chloride, and so non-actinide systems, and see what methods are appropriate to use for them to get good predictions. And once we have benchmarked those, we're going to start mixing them with uranium trichloride and see what we can learn from that. Obviously, we're far from the first ones doing these kind of simulations, so I'll give you a reference to the relevant literature as well, and we're obviously building from what has already been discovered in the literature. Even though my focus will be on somewhat simple properties such as density and mixing energies, heat capacity, those are still very important for MSR developers and designers. And the fact that they are simple doesn't mean that they are always well characterized, or there's still important knowledge to be gained there. And the final point I want to make here is that although we will focus on the sort of pure or binary or ternary systems, the fuel cells here, the real value of this simulation approach comes when we start adding chromium and fission products to this. You get a more complex composition space that is difficult to fully cover with experiments. So let's get into the results. So this slide shows predictions for density and heat capacity of sodium chloride. So methodology that was used here was ab initio molecular dynamic simulations. We used supercells, so a system containing anywhere between 64 and 216 atoms. And the big range there is because we wanted to benchmark how many atoms we needed to get good results. Obviously, the 216 atoms simulations are much more expensive than the 64 atom simulation. So if you can get away with a smaller number, that's much preferred. I think I'm going to stay away from describing all the technical details here, but in short, we use what is called the PVE, exchange correlation potential. We use dispersion forces in our simulation. So that's describing van der Waals interactions, which isn't part of standard DFT simulations. We try out a few different approaches to describe that, and that does influence the results. So it's an important exercise to benchmark your simulations and see how well various dispersion force models do. The simulations are done in constant in a constant pressure simulation environment in order to be able to predict density. Constant volume might be more appropriate for some cases, and my collaborator at NC State, Ben Beeler, sort of done the corresponding simulations to me with that approach. I won't show that here today, but we're exploring that as well. So if you look at the results here, you can compare predictions of density and heat capacity to experimental correlations. And you can see that we do really quite an excellent job. In terms of heat capacity, we're within a few percent, and density, is also within 5% of the experimental measurements. If you don't use the right methodology, meaning if you don't include van der Waals interactions, so dispersion forces, you will get the yellow results at the bottom, which differ from the experimental results shown in the orange line here by 10 to 20%. So this just emphasizes that you can model these molten salts quite accurately, but you do have to pay attention to the methods used. Otherwise, you may get results that aren't so good. You can also look at these simulated data points, and although they are not at a perfect line, they are all pretty close to a linear dependence on temperature. So that's all very both for density and heat capacity. So that gives us confidence both in the simulation approach as well as confirms the experimental correlations, which all indicate the linear dependence. So I did mention that we looked at simulation cells of different size, and this plot to the left, lower left here, shows the radial distribution function obtained with a small cell containing 64 atoms and a larger cell containing 216 atoms. And you can't really distinguish the lines because they essentially predict the same results. So that gives us confidence that at least for the pure sodium chloride system, the properties should be very well described with the smaller cell. So that's the cell we're going to move forward with, because it does save us quite a bit of computational time. The same comparison is done for an actual physical property, in this case density, in the upper right here, and you can see that the predictions with the small and large cells are almost identical. That's the orange versus the blue dots here. There is some deviation at higher temperature, which is higher than we are really interested in. So we didn't spend too much time or figuring out what causes that. But at these intermediate to low temperatures, we're confident in the ability of the smaller cell to predict the right behavior. There is a little bit of caveat to that, and that is when we go into looking at the mixed system, because for example, sodium chloride, uranium trichloride, I will later explain how the behavior of that system is driven by shifting chlorine ions towards the uranium ions and changing the pair distribution function or the radial distribution function around the uranium ions. And that tends to drive reconfiguration of your cells. So you may end up distorting your cells and ending up in simulation problems if you have too small cells. So that's something to watch out for, and that's something we ran into. That doesn't have so much to do with reproducing the right radial distribution function as it has to do with distorting your cell to unphysical shapes if you're not careful. So that's just something to keep in mind if you were to pursue this on your own. So I showed you the results for sodium chloride. Potassium chloride is obviously expected to be very similar. We applied the same simulation methodology, and you can see the results from those simulations for heat capacity and density in the two plots at the lower end of the slide, as well as in the table here. And again, the agreement with experiments is very good. The discrepancies are of the same order of magnitude as for sodium chloride. We can also see that if we compare sodium chloride, which is yellow here, the calculated values, to the predictions for potassium chloride, the difference between the two are very close to the difference observed in experiments, although I don't show the experimental line here. You'll have to trust me on that one. So that's again nice results. We are getting good predictions if you use the right methodology, and we are within the sort of 5% range of experimental measurements for both heat capacity and density. So having gained confidence in our ability to describe simple salts, we take the next step and start doing the same type of simulations for uranium trichloride. Uranium trichloride is, of course, expected to be a bit trickier because it involves uranium with all its F electrons and so on. And speaking about uranium and its F electrons, for people like me who come from a solid state background and did a lot of simulations of uranium-based fuels, such as uranium oxide, we know that the standard approaches to do DFT for those systems is imperfect. They do tend to predict systems that we expect to be insulators to be metals. For example, if you did standard DFT for a molten uranium trichloride salt, you would predict it to be a metal, which is obviously inconsistent with the nature of a salt. In order to improve that description, there are several approaches, and one of those is what we call a Hubbard-U model, and it's computationally fairly inexpensive to use that model. So that was the choice we made here, and if you use that, you do predict the correct insulating behavior of the salts. So that methodology will be used moving forward in everything I show. So using that and the same type of simulation approach, again, we try different sizes. Most of the results I'll show is for a smaller cell here to save computational time. We predict density as well as heat capacity. There are less data for uranium trichloride than for sodium chloride. Heat capacities are in very good agreement with estimates done in development of CALPHA databases. That's again within 5% and even less. Density are in good agreement of experiments depending on which experimental data set you compare it to. Historically, there are two sources. There is one correlation presented by NEAMS and one from Russian studies by Dysyatnik and collaborators. And the calculations agree very well with the green line here representing the Dysyatnik data and very poorly with the other correlation. So I think this is known by the community already, but this clearly highlights that the Dysyatnik correlation seems much more reasonable if you trust the simulations, and there is no reason why the simulations would be off by as much as the difference between Dysyatnik and NEAMS here. And in fact, if you look at how accurately we predict density for uranium trichloride with the methodology we used here, we are actually even a little better than we were for sodium chloride. So that's very encouraging. Same thing with heat capacity. I showed that briefly in the previous slide, so I think I'll skip any further discussion about that. I'm only gonna show this slide very briefly because this is very much a work in progress. We also studied uranium tetrachloride. It was more challenging to perform these simulations for technical DFT reasons. It was simply hard to get them to converge in many cases. And the fix that we found was to include spin-orbit coupling in those simulations. That made them computationally more costly, but the results coming out of them were consistent and the simulations converged. And again, I compare here very preliminary predictions of heat capacity and density. And there are some differences for density compared to experiments, but they're all still pretty close, and we capture the fact that uranium tetrachloride has a lower density than uranium trichloride. We've also studied, I clearly spelled the heading wrong here, so the AlCl3, aluminum trichloride, and using the same methodology as I've already shown you. Aluminum trichloride is very different from the previous systems. It has a very narrow, molten aluminum trichloride has a very narrow stability range. It boils at, I think it's like 700 K or something like 800 or 700 K, and it melts at like 500 K. So we tried to cover that range here, and we can see that we haven't really gotten as good results as we did for the other systems. It's related to the very sort of molecular nature of these molten salts. We can see that there's a big discrepancy between the available experimental correlation. This correlation is based on only 2 data points that were a few Kelvin apart. So it's one of those where it would probably be worth remeasuring it. Nevertheless, these are the results we got, and we'll continue to pursue this and try to understand the behavior. But the complexity of this system and its low melting point and the corresponding difficulties in the simulations meant that we're not able to look at this system mixed with uranium trichloride. So instead of spending more time on that, I'll go into looking at the properties of mixed sodium chloride and uranium trichloride, and we'll start with density. So what was done here was to take the same simulation process we used for the binary systems. We added uranium trichloride to the sodium chloride. We ran these simulations and extracted densities and energies as function of temperature. And the plot to the left here shows density as function of composition for 3 different temperatures. The actual calculations are shown by circles, and the lines are the corresponding experimental data. The plot to the right here shows the deviation from ideal solution behavior for both the calculations, the solid lines with the dots, and experimental correlations coming from Dysyatnik, the same Russian reference as I talked about for the pure system. And it's easier to sort of analyze this deviation, the fractional deviation from ideal solution behaviors. So I'll talk about this plot in some more detail, but it basically contains the same information as to the left. We can see that, so a value of 1 here corresponds to ideal solution behaviors and no real interaction between the ions. And we can see that both the simulations and measurements predict the minimum close to a fractional concentration of 0.3 or so. The simulations predict a deviation of about 2% at this minimum. There isn't a strong temperature dependence really, while the experiments predict up to 5% deviation, and they do seem to show a stronger temperature dependence. The one temperature dependence we see is for the higher 1500 Kelvin simulations, where in on the uranium-rich side of the system, we get a positive deviation by 2% between 50% uranium trichloride to pure uranium trichloride, but all the other temperatures show a consistently negative deviation from ideal solution behavior. So if we plot, actually, here comes the same. Let's see here. Okay, here comes the same results for the potassium chloride system. So we did the same type of simulation. So if we focus again on the deviation from ideal solution behavior, we plot the results for potassium chloride and uranium trichloride in blue. And then we have the corresponding experimental data again from Dysyatnik in yellow, and the prediction for sodium chloride and uranium trichloride in gray. And there's another experimental correlation here that obviously disagrees with everything else and probably shouldn't be trusted too much. So we do predict that the deviation from ideal solution behavior is about twice of what we saw for the sodium chloride system, which is consistent with what experiments show, although the experimental data for sodium chloride, uranium trichloride was a bit lower than our prediction. So it's not quite double the deviation from ideal solution behavior, but the trends are still captured. So with that, I'll go to the next slide, which shows sort of the same simulations, but instead of looking at variations in density, we're looking at variations in mixing energies. And I'm actually showing two data sets here, and I'll start talking about the one to the left here, and I'll say a few words about the one to the right after that. So the mixing energies are, as expected, pretty low per formula unit. They go down to about 0.07 or 0.08, a little bit depending on temperature, EV per formula unit. Again, we can see that there is a minimum somewhere in the 0.3 to 0.4 atomic fraction of UCl3. We can see that, while we didn't see a strong temperature dependence for density, there seems to be a little bit of a temperature dependence with the lower mixing energies predicting for the lowest temperature, and then they go up a little bit with temperature. But it's not a strong temperature dependence. There are actually some experimental data, and I guess I must have, by mistake, deleted the reference for those experiments here, but it's a paper from France that was done a few years back, and those are the yellow points here, and you can see that the agreement between our predictions, the experiments were at 1100 Kelvin, and if we compare those to the simulations at the same temperature, it's really a remarkably good agreement. And we also see the red line here, which is the correlation or the model used in the most recent CalFUD assessment of the system. The CalFUD assessment does not have any temperature dependence. It was based on basically the experimental data here. So those measurements were only performed at one temperature, so they assumed that it was a constant. The deviation from ideal solution, from the mixing energy or solution energy was basically independent of temperature. We see that the simulations predict a weak temperature dependent there. So that's a little bit of extra information that we were able to tease out of these simulations. The caveat here is that the results from the simulations, they do depend on fairly, if you change the reference system, so if you change the energies of the pure uranium trichloride and pure sodium chloride systems a little bit, then the temperature dependence that you can tease out here changes as well. And you can see here, this is an earlier estimate, but we haven't quite refined those end-member simulations perfectly. And you can see that that would have predicted no temperature dependence. And to be perfectly honest, we're still working on refining whether, and to understand whether the left-hand figure or the right-hand figure is the best answer. I do favor the left-hand figure, that's why I started out there, but you could probably argue that the difference between the left and right-hand figure is within the uncertainty of the simulations. So next we'll look at the same properties for potassium uranium trichloride mixture, and again we did exactly the same approach and same methodology. And this plot here shows the mixing energy as compared to the most recent CalFUD assessment of the potassium chloride uranium trichloride system, as well as the simulations for sodium chloride and uranium trichloride in gray. And you can see that the deviation from sort of mixing energy and anything negative, it means that it deviates from an ideal solution behavior. And similar to the discussion for densities, the deviation is about twice of what we observed for the sodium chloride system. And again, this the minimum is pretty close to 0.3, 0.4. Interestingly, you've now seen that we observe very similar behavior in a minimum and a similar location, and this minimum is located at the same location as the geotectic point in these systems. So that's an interesting observation. We have only calculated one temperature for this system now, so we can't say anything about the temperature dependence of these properties yet. You should also keep in mind that the result for potassium chloride we haven't converged the results quite as good as the sodium chloride, uranium trichloride. So please keep that in mind. Going back to the sodium chloride, uranium trichloride, where we perform more simulations as a function of temperature, we can analyze that data and learn a little bit of how the temperature dependence changes with composition. And in the two plots at the bottom left here, you see how the energy and how the density changes with composition as we go from pure sodium chloride to pure uranium trichloride. In each case, you can see that although we don't have too many data points, that the dependence seems to be follow a very nice linear correlation. There is these data points and the linear polynomial fitted to them, they fit the data points really well. Same thing for density. If we look at each of these fits and we extract the temperature dependent coefficient, for energy, that means the heat capacity, and for the density, it's a parameter related to thermal expansion. And if we look at the heat capacity first, that's the top plot here in this slide, you can see that the points scattered a little bit, but mostly this is a linear correlation as function of composition. So the heat capacity seems to pretty much follow an ideal solution behavior, even though the mixing energies did not, as shown in the previous slide. If we look at the temperature dependent of density, it is not quite a linear correlation. You can see that it's almost a parabolic behavior in the sodium chloride rich part of this plot, which is to the left, and then the correlation switches and goes above the straight line in the uranium trichloride rich system. And this is related to the sort of deviation I showed for the density at the highest temperature in the uranium rich region. So I haven't emphasized sort of that this is not quite a linear correlation, which is true. It's still not a big deviation for a linear behavior. And yeah, we need more experiments to say whether this is an accurate prediction or if it's within the uncertainty of the simulations. I tend to think that we actually have enough accuracy in our simulations to tease out the correct behavior here. In the results I've shown you for the mixing energies and the densities, you've seen, I should have had an introductory slide here showing how that depended on composition, but I'll remind you verbally. For all cases, we saw a negative deviation from ideal solution behavior with a minimum close to the eutectic composition of 0.3 or 0.4 mole fractions of uranium trichloride. And we figure that this must be driven by some of the local chemistry. So if we carefully study the radial distribution functions for this system, we should be able to probably explain this behavior. And it turns out that that's the case. And some of this was done in the literature already, or at least part of this problem. So if you start with sodium or with uranium trichloride, as you add sodium chloride to uranium trichloride, the chlorine ions will tend to move towards uranium ions. And you can see how so the first blue line here indicates the radial distribution function between uranium and chlorine, and the peak of this blue curve here increases as we increase the concentration of sodium chloride. So that means we're adding chlorine ions to that coordination shell, and we do see how that decreases or sort of gives you a negative mixing energy. So this is a favorable coordination. Now, we also saw that the mixing energy, as well as deviation of density from an ideal solution decreased until you got to about 0.3. So here that would be somewhere around the B plot 0.29 and C plot 0.36. And one noticeable difference between those, or what happens between C and B, is that if you look at the yellow line here, this represents the uranium-uranium correlation in the system. So the radial distribution function between uranium ions. And the dotted line, or the plus signs here, represent what that correlation looks like in pure uranium trichloride. And almost somewhat amazingly, that even when you've added more than half, or you've replaced more than half of the uranium trichloride units with sodium chloride, the uranium-uranium radial distribution function is mostly maintained in the system. And that's a sign of this correlation being favorable, so the system rearrange it, but it works really hard to maintain that correlation. However, when you go to decrease the count of uranium trichloride just a bit more, the system is no longer able to maintain that correlation. And you can see that the yellow line here now deviates from these plus signs. So this really, or more or less exactly, corresponds to when we see passes the minimum in the solution energy. So we believe that solution energy and its deviation from an ideal solution behavior, as well as the density, is driven by the increase of this first peak, and as well as how that competes with the uranium correlations here. So we think that's a quite an interesting observation. And the last point I wanted to make here is that in a solid state system, if you have a negative mixing energy between two compounds, typically that means that you have stronger bonding in your system and the volume contracts. That means that the density increases. For these mixtures, we actually saw the opposite relation. So the energy was negative, so that means the system was binding stronger, but the volume increased and the density decreased, which led to this negative deviation. And the reason why it's doing that, we believe, is related to the evolution of more chlorine ions around the uranium ions. Although that is not exactly a transition to UCl4, it kind of mimics that system, and the UCl4 density is lower than for UCl3. So we think that it's that underlying physics and chemistry that explains why the density decreased instead of increased for the mixed system. So with that, I've come to my conclusions and summary slide, and hopefully I was able to give you a little bit of a taste of the work we've been doing to apply ab initio molecular dynamic simulations to actinide-containing chloride salts, and I showed results for sodium, potassium, and aluminum trichloride. If you use the right simulation methodology, we can get quite accurate predictions for densities and heat capacities, and they compare quite well with experiments. There are some exceptions, aluminum trichloride being one of them. And some of the experimental data, the ones from Jans for UCl3, they seem to deviate from our predictions, but that's probably related to a measurement inaccuracy, we believe. Most of the mixed salts were predicted to be close to an ideal solution, but still with a noticeable deviation for both densities and mixing energies. And we were able to correlate those deviations, negative deviations in density and mixing energies with the evolution of the pair distribution functions. We were also able to predict the differences between potassium chloride mixed with uranium trichloride as compared to sodium chloride and uranium trichloride. The last thing I wanted to mention was sort of the extension what we've been doing here for density and basic thermodynamic properties to more complex thermophysical properties such as viscosity and thermal conductivity. Those are really too expensive to obtain with the ab initio methods that we've been using here. So with collaborators at LANL, we're developing density functional tight binding models which retain some of the chemical flexibility or chemical accuracy of traditional DFT methods that I was using here, while being much faster. And we're developing those currently for UCl3, UCl4 in order to test our ability to describe both uranium-3 and 4+ at the same time. And after that, we'll add sodium chloride and other elements to extend those simulations to systems of more interest for reactor applications. I should say that the DFTB approach taken here is something that we believe in, but there are many efforts at universities and other national labs pursuing machine learning potentials as well for these similar kind of applications. And although they are different, they target the same problem, that many of the more complex properties are simply too computationally expensive to address directly with AIMD simulations. And although I didn't describe too much of it here, I would like to emphasize my desire to work closely with experimentalists, because the need to validate predictions and work together to derive better models and help reactor developers. It's really a collaborative effort that needs to accomplish that. So I always like to end with that statement here. So with that, thank you all for your attention, and I'm happy to take any questions.
So thank you, David, for the nice talks. A lot of data, and then very rigorous. Any questions from the audience?
Can I ask a quick question? Adrian here.
Yep.
Yeah, so to your opinion, David, first of all, thanks for the great presentation and the work you're doing to extend the experimental data to meaningful data set that can be used by the developers. My question is about how, to your opinion, what are the validation data that you need the most at the moment? For instance, the kind of cell properties that you're able to predict, but lack a significant amount of validation data, and you'd like the experimental community to work on that.
So I think on top of my list would be to measure radial distribution functions as function of composition, and see if the change in features that I was pointing out close to the eutectic composition, if they can be confirmed in experiments. I think that would be quite interesting, because that's sort of at the heart of the mechanism identified to explain the property of evolution as functional composition. And the other one would be densities as function, good measurements for densities as function of temperature, and see if there is a temperature dependence or not on how that evolves, and the same thing for mixing energies. And some of those measurements are underway by collaborators, but it's hard to do them with the uranium in your system, because you need all the corresponding approval, even if it's based on depleted uranium. But those would be on top of my list for my own interest. I think if we look at the work that NEAMS is doing at the systems level, I think corrosion measurements and understanding corrosion behavior, or how these salts interact with the alloys used for constructing the reactor, would be probably of an even higher importance.
Okay, thank you. And just to follow up, are you planning to look at the effect of, try to model using the same kind of techniques, try to model the salt metal interface a little bit? Is that something that you like to pursue in the future, or do you want to stay within using the same kind of modeling technique, but only for physical properties of the salt in the bulk form?
So it's definitely of interest. It's not in the current plan, just because there is enough scope to pursue here at the moment. And I think, and you are well aware of the IRP call that is out, for example. I think topics like that could be something, I think it would be looked on favorably if that was potentially addressed within a call like that. I mean, I have no part in selection of that, but there are many people in the university community that are excellent at those problems. And I think that would be something good to pursue by our collaborators at the universities.
Okay, thanks a lot.
Right, I want to invite more questions, please.
Yuvan, can I ask one question?
Yes, please.
Okay, yeah, very nice talk. I have one question about the initial you are studying the uranium chloride. You cite, as we know that the DFT maybe is not good and to predict the band gap like the DOS as you show here. But I'm wondering that when you consider the DFT plus U, this method, have you used this method in the AMD simulations? And when you predict the density of the PRD and like that kind of parameters?
Yes, so we used the Hubbard-U model for the AMD simulations for the salt densities, and the densities go down. So the volume goes up and the densities go down as you add the U compared to if you don't add the U parameter. Does that answer your question?
Yeah, it answers my question. So another thing that how large is the difference when you plus U in the AMD, the density change?
Oh, that's something I should remember, and I don't remember that off the top of my head. It's not a huge difference. I think it is roughly in the same. It's a little less than the 5% that I highlighted as a discrepancy between experiments and simulations. So it's of the same order of magnitude as that, if I remember correctly.
Okay, thank you. Thank you for the question.
Are there any other questions?
Oh, I do have a question.
Please.
Yeah, thank you for the excellent presentation. This is Xiao Chin. I'm currently a PhD student working with YZ's group at UIUC. So I'm wondering if there's any methods that you can use to infer or say something about new compositions based on the current database you have developed from now.
Yeah, so certainly we could, you saw basically the correlations we fitted to various properties as function of composition, and you can certainly use those to fill in gaps between data points fairly accurately. I think what you're referring to would be very interesting to use the data generated and apply it in a machine learning framework and see what you can capture and learn about that in terms of various descriptors and so on, and see how that extends to completely new salt systems. We haven't done that. I think that would be something very interesting to try, but we haven't done it and we have no immediate plans to do it. But it's a good it's a good question to ask and an interesting problem to pursue.
Thank you.
Okay, I think we have time for more questions. David, I have a quick one. So for all the calculations you have, it's all chloride. I wonder if there any justification of choosing chloride at this moment?
The answer is simple. Your old colleague Chow at Idaho focused on the fluoride system, and I focused on the chloride systems to start.
Oh, I see.
And then I focused a little bit more on the actinides as well. So that is one reason for that choice. The other one potentially being that there is less data for the chloride systems, as I understand, than the fluoride system. So the need to do simulation was perhaps better motivated for that. That also caught my attention and made me gravitate towards starting on the chloride systems. And those chloride systems are considered, my understanding is for fast reactor applications like the designs that TerraPower has for their molten salt reactors, for example. Historically, I think fluorides were used in the old Oak Ridge experiments and the old molten salt reactor experiments that took place there in the 60s. 60s and 70s. So yeah, that's the reason for focusing on chlorides. That doesn't mean that chloride is better than fluorides. It's just where I gravitated to start.
Yep, thank you. Do we have more questions from the audience? I don't want to use up all the time for my own questions.
I have a question. Thank you, David. That was a really interesting talk. This is Ben Lindley, an assistant professor. So in the chloride space, I guess there's rather a lot of different chloride salts that might be of interest for advanced reactors and things like pyro reprocessing. How wide do you intend to go with these simulations? You've looked at quite a range already with uranium chloride, sodium chloride, potassium chloride, but then you think some people look at magnesium, some people look at plutonium chlorides. Do you intend to go to a big broad range of these salts?
Yes, that is all of interest, and maybe I'll state out the priorities to answer your question. I think all the compositions you're describing are all of interest. Of biggest interest to me is probably to add plutonium chloride to these simulations for some of the base salts, just because plutonium chloride is so tricky for labs to handle, and there aren't very many labs that would be able to do it. So I think we would be able to provide the biggest value with our simulations there. So that would be the motivation to go after that. Before extending it to more sort of base salt compositions, I would probably also add chromium chloride with the intent of looking at the effect of corrosion products. So before covering the full base salt composition, see what we can learn for corrosion impurities and corrosion products, as well as some of the more important fission products. Does that answer your question?
Yeah, that makes sense. Thank you.
I think we can still take another quick question. Okay. Well, if there's no other questions from the audience, I will conclude the meeting here. And thank you, David, for visiting us virtually and give this very nice talk. And hopefully we can get you here on site sometime.
Thank you all for the invitation, and thank you all for attending and listening to me. Have a good afternoon.
Yep, I'll see you in a while, David.
Bye-bye.